Electric.
All right, let's
And
do potential difference today. So we learned before the current, electric current. You still remember what it is? It is, right?
yeah.
So potential difference. So we'll just review the thing that we did before. So basically, if you have, let's say you have a battery, okay? It transforms chemical energy to electrical energy. All right. So there's a reaction, chemical reaction going on inside the battery, okay?
Mm-hmm.
And so let's just say if there's a battery like this, there's always going to be a positive and negative side of that battery. And if you use the battery, you trigger a reaction inside the battery. So there will be a buildup, a surplus of electrons at one of the terminal. Of course, there's going to be a lot of electrons at the negative side, the black one here.
Mm-hmm.
And it creates a shortage of electrons in the positive side because all the electrons just move away from this one, right? It just move away. All the electrons just move away to the negative side. And so the positive one is like nothing there. There's no electrons there.
So that's the meaning of no more battery.
Listen to me first. When there's a chemical reaction going on inside it, the electrons will build up at the negative side, and there will not be electrons over there.
Mm-hmm.
But then it's then able to maintain a flow of electrons. So the flow of electron, it's electric current, right? And if you connect the battery into any circuit
Mm-hmm.
across the terminal, like positive and negative one, then there will be an electric current flowing through that wire as long as the chemical reaction lasts. So it means that the battery will not last forever. The reaction will have to stop at one point, isn't it? And when it
Mm-hmm.
stops, your battery becomes useless. You can throw it away. With a
I see.
rechargeable battery, you can recharge it many times. Like for example, the battery on your phone or in any other equipment, you can recharge it, right?
Mm-hmm.
But there are some battery in which you cannot recharge, and if you try to recharge, they will explode.
Really?
Anyway, so the battery is said to have a potential difference, or PD, at its terminal. Potential difference is measured in volts, and the term voltage is sometimes used instead of PD. Let's just say
Mm-hmm.
that with the potential difference of, let's say, a car battery is 12 volt. This one, you can find it in the car, and it's often like 12-volt battery.
12 volts.
That's the battery for cars, okay?
Wait, I
But
thought cars are used by gas. Is this for electric cars?
even though cars use petroleum to run, but there's some electronic components that need battery. For example, the trigger. Like for example, that your you trigger your car to operate. You need a battery, right?
Mm-hmm.
Mm-hmm. So it has 12-volt voltage difference.
Mm-hmm.
For domestic main supplies, in the UK, it's 230 volt. In Vietnam, it's 220 volt. In
220.
Japan, it was 110. How much is Singapore?
Um,
Singapore voltage.
like 200?
It's
200. Oh, yeah,
230,
200.
230. It's
Mm-hmm.
230 volt. Okay.
Mm-hmm.
And let's read the other ones here. In an electric circuit, electrical energy is supplied from a source. You need a source, of course, such as a battery or electric socket. And it's transferred to other forms of energy by devices in a circuit. So basically, you are provided an electrical energy the flow of electrons, yeah? And depending on what you plug it to, it will transform into, let's say, if you plug it to a light bulb, it will transfer into light energy. If you plug it into, let's say, a water kettle, then it transfers into heat, right?
Mm-hmm.
Something like that.
I
Let's
see.
say a lamp, okay? You connected a lamp to it. It produces both light and also heat. Because when
Mm-hmm.
the lights heat up, when the light bulbs or a lamp heat up, it produces also heat too. You can see it's really hot, isn't it?
Mm-hmm.
Okay, beside from the light. Okay. Now, so when each of the circuit in this figure, 37.1, is connected up. Okay, so here, let's see. Here they connect this
220
lamp.
volts.
This is a 100-watt lamp, really bright one, okay? It's connected to electric sockets. So two 30-volt mains.
What does what do they mean by the term
Well, it's a
mains?
main source of electricity that our home also is using, like electric sockets, the one you plug in it, the main one that every device in your family is using. It's called a main. All right. And the lamp here, it's a main lamp, it's 100 watts, really bright one. And it's connected to an ammeter, you can see here.
Mm-hmm.
Okay, and the ammeter is in turn connected to the main again. So you can see that this is one circuit. On the right side, you also have ammeter, and here is
What
a
does
six.
ammeter do again? I forgot.
It is something to measure how strong the current is,
Oh, okay.
how many ampere, how strong the current is.
I see.
Okay, and here this ammeter is connected to a car, a side lamp of a car,
Mm-hmm.
which is 6 watt only. And here is connected to a 12 volt
Is
AC
6 watts
supply.
powerful?
Sorry?
Is 6 watts powerful?
Nah, not really. It's really like, what is this? A car side lamp. Let's check it out. Here, you have a car. Okay, this is a side lamp, okay? Okay, it's not exactly too bright to be honest with you, but it's enough to to illuminate something in the dark, isn't it? So that people won't bump into you, crash into you on the road. But anyway, this one is connected to a 12-volt AC supply, which is the battery of the car, isn't it?
Mm-hmm.
And of course, this one is connected to ammeter, so it's like another circuit here.
I
Okay,
see.
right. And of course, if you compare the two, the left and the right one, in terms of energy, the main lamp it transfer a great deal more electrical energy in a second than the car lamp. Of course, because it is connected to two 30-volt mains, right? But this one is only 12 volt. So it means this main lamp, in 1 second, it transfer a lot more electrical energy into light energy, isn't it? Compared to only 6 watt, isn't it? Have you ever seen a 100-watt lamp? It's really, really strong, okay?
100 watts.
Yeah, a
Super.
100-watt lamp is just really, really bright.
I see.
Like one bulb like that, you can illuminate the whole room.
Like one room,
Yeah, one whole room is
you
like a
can
big
light the
one.
whole with what that 100 uh watts light,
Yeah,
bulb
it's
light.
really bright. It's really bright though. It's just
Is it
truly
really?
bright.
That's very bright.
Mm. And let's just say here. Let's say in the dark and you have 100-watt lamp, the whole room actually lit up a lot just because of one bulb. All right, but the problem is the higher the wattage or the higher the watt, of course, the lamp consumes much more electricity and you have to pay more money for it,
Mm-hmm.
compared to a 6-watt lamp. So
Mm-hmm.
let's say if the watt is really small, then it doesn't consume much electricity. Okay, let's compare. A water kettle. There you go. So a water kettles can be up to 1,500 watt. What does it say?
1,500 watts,
Yeah, so does it consume a lot of electricity?
of course.
Very much. So anything that boil, that cooks, consumes so much electricity. So,
Why don't you use fire?
sorry.
Why don't you use fire like petrol, like gas?
The problem is those things are not safe. They are unsafe because petrol actually produce CO2 gas inside your home. You don't want to get suffocated. And also they smell bad. Petrol smell bad inside the home.
They do.
They do. They smell very bad inside the
I
home.
like I like the smell of petrol.
No, you do. I used to, but it gives me headache.
It doesn't.
Anyway, you know what it means.
Every time when I, every time when I enter the car park, there's always
Hmm.
this smell of petrol.
Okay, you know an air fryer?
Yeah.
Of course. Okay, you can look at what they say
Oh,
here.
it's not 1,550.
Yes, 1,550 watts. So it means it consumes
No
so much
wonder my
electricity.
no wonder my mother electric bills are so high.
It's really high. So you have to be careful, okay? The higher the wattage, the more electricity it will consume. Okay, you
If
understand
you,
it now.
I see.
Mm. So basically, we human have tried to reduce the electricity bill somehow. So we don't use a traditional light bulb anymore. We now use energy saving bulbs. Okay, like these bulbs can now be only like 7 up to 12 watt, but they produces
Of what?
almost the same amount of light as a traditional light bulbs. Okay, so
7 to
it's
12
sorry,
what? Is it 7 to 12?
around that, yeah,
That's so less.
yeah, but because they are energy saving, they produces okay, they consume much less electricity, but the amount of light produced is almost the same as the traditional light bulb. So it's much better to use them. Like for example, you look at this one. Okay, they say 8 watt of
Oh,
energy, but equal to a 40 watt of the traditional light bulb, isn't it?
I see.
Mm. So it means your electricity bill will go really down if you use these energy saving light bulbs. Okay, there is one thing that you can use the traditional light bulbs for. Okay, traditional. These traditional light bulbs, only 5% of the electricity it eats up is used for creating light. So what does it mean? 95% of that electricity is going to be used to create heat. So it means if you're in a cold winter days, if you're in a cold winter's day, these light bulb can help you heat up your home.
Mm-hmm.
However, we are living in Vietnam now. It's really hot, isn't it?
Is there light bulbs that make it cold? Like
Oh, yeah, but we're in Vietnam, in a tropical country now. We don't need that heat, right? We just need the lights. So that's why just use energy saving light bulbs, okay?
I see.
Okay, let's move on to this one. All right. Evidently, the potential difference or the voltage across a device affect the rate at which it transfer electrical energy. So what does it mean? So let's just say 100-watt lamp will transfer much more energy in 1 second than a 6-watt lamp. Is that true?
I don't know.
It is. Let's say 100-watt lamp will eat up a lot more electricity in a second compared to a 6-watt lamp. So the same thing happened to all the other devices you have, you know? Okay, and that's the rate at which it transfer electrical energy in any device you have. Okay, this gives us a way of defining the unit of potential difference, the volt. Okay. Now, can you read the model of a circuit? This one, please.
You stop.
Can you just read the model of a circuit here?
It may help you to understand the definition of the volt, i.e., what a volt is. If you imagine that the current in a circuit is formed by drops of electricity,
Mhm.
each having a charge of 1 coulomb and carrying equal sized bundles of electrical energy. In
Mm.
figure 37.2, Mr. Coulomb presents
Represent one such drop.
presents one drop as a drop moves around the circuit, it gives up all its energy, which is changed to other forms of energy. Note
Mm.
that electrical energy, not charge of or current, is used up.
Just look at this one. You see, here's a battery. So at the start, Mr. Column here carry a lot of electrical energy, right? And
Mhm,
as it moves along the wires, you see the back is getting a bit smaller. Why? Because the wire itself consumes some electrical energy, right? And as Mr. Column passed through the lamp take away a lot of electrical energy. So now he has only a little left, isn't it?
mhm,
And then he returned to the battery with nothing. It's a way to look at it, okay?
mhm,
But still, it's the same current that running through the lamp, isn't it?
mhm,
But it just the electrical energy that it consumed, not the charge of the current, because it's still the same current. It's just electrical energy that is eat up, that's eaten up, it's used up. Okay, you understand it now?
yeah.
Right. All right, let's read this one. Can you? In our imaginary representation.
In our imaginary representation, Mr. Cole
Representation.
travels round the circuit and unloads energy as he goes, most of it in the lamp. We think of him receiving a fresh bundle every time he passes through the battery, which suggests he must be traveling through fast. In
Mhm.
fact, as we found earlier in chapter 36, the electrons drift along quite slowly. As soon as the circuit is complete, energy is delivered at once to the lamp, not by electrons uh, directly from the battery, but from electrons that were in the connecting wires. The model is helpful, but it's not an exact representation.
Representation. It just to help you understand what is being eat up, it's the electrical energy that is being used up. Okay. Now let's move on to the volt. Okay, so you know some batteries like 3 volt, 1.5 volt, some's like 6 volt, 9 volt, something like that, you know? Now, okay, so this demonstration here show that the greater the voltage at the terminals of a supply, the larger is the bundle of electrical energy given to each column, and the greater the rate at which light and heat are produced in a lamp. So let's just say that here you have 230 volt, but here you only have 12 volt. So of course, the one on the left here will transfer the electrical energy much faster to the lamp, right? Compared to the one on the right, isn't it?
Mhm.
Okay. So the potential difference between 2 points in a circuit is 1 volt. If 1 joule of electrical energy is transferred to other form of energy, when one column passes from one point to the other. So it's trying to explain this one. 1 volt equal to 1 joules per column. So let's just say that, okay, you have a circuit like this between point A and point B. You have two battery, okay? So it means in total, point A and B, the difference is 3 volt because they combine together.
Mhm.
So what is volt? 1 volt equal to 1 joules of electrical energy transferred to other form energy. When
Isn't it the
one,
same?
yeah,
Isn't volts and joule per column the
yeah, it's the
same?
same thing. Yeah, it's trying to explain this one. Yeah, 1 volt equal to 1 joules per one column. Yeah. So let's just say if 2 joules are given up by each column, the PD is going to be 2 joules divided by C. So it's going to be 2 volt.
I
And if
see.
6 joules is transferred when two column pass, you have 6 divided by 2. It's going to be 3 volt.
Mm-hmm.
Mm. So, so in general, if energy in joules is the energy transfer when charge Q in columns passes between 2 points, the potential difference in volt between the points is given by this. Volt equal to energy divided by charge in column. Or you rearrange this one. You can have E equal to Q times V, right? Isn't it?
Mm-hmm.
Okay, it's important to write down this one so you understand the concept. Now,
Yes.
if Q is in the form of a steady current I amperes following the time t second, then it's basically Q equal to I times t. You know, the flow of electron is Q, the current is the I, and how much time it passed through is t. So you have Q equal to I times t. So you can replace this one with a Q here. So you have E equal to I times T times V, isn't it? It's just playing around with the formula.
Mm-hmm.
Okay, please write them down, otherwise you forget again.
Okay.
Now, the next part is cells, battery, and EMF, electromotive force.
Mm-hmm.
So a battery consists of two or more electric cells. All right, what's inside a battery? What's inside a battery? Now, if you have a piece of battery and you open it up, there's going to be a lot of things inside.
What is it inside? Is there gonna be like liquid or something?
No, not really.
Or any rocks or anything?
It depends on
Oh,
what kind of battery, but inside a 9-volt cheap battery, you can have like a lot of rods like this. And okay, why am I even explaining the inside battery? But there could be a lot more smaller battery connected in there, you know.
mm,
Anyway, so a battery can consist of a lot more than just two. There could be like 6, 7, 8, 9, 10, whatever electric cells in there.
mhm,
Greater voltages are obtained when cells are joined in series, not parallel, okay? Series. Like for example, this one. If you have a battery and you connect to another battery here, so let's just say you have 10 battery, it's going to be 15 volt, isn't it? This is connect in series, okay?
mhm.
But if you connect in parallel, it doesn't work the same way.
I see.
Okay, let's look at this figure, 37.48. This one I'm trying to explain. If you connect them in series, like look at this one, positive, negative, connect to the positive, negative, connect to the positive, negative, and so on. If you have two of them in series, the total is going to be 3 volt because they combine in series, they combine.
Mhm.
Now, every column in a circuit connected to this battery will have a 3 joules of electrical energy. Because why? 3 volt means 3 joules per column, right?
Okay.
If you use this formula,
1 volt equal 1 JC.
yeah. So it means 3 volt equal to 3 joules per C, right?
Mm-hmm.
Yeah, that's what it means here. That's what to say here. So the cells in figure 37.4b, this one, are in opposition to the voltage, and the voltage of X and Y is 0.
Which one is the plus?
Look at this one. So basically they are connected in the opposite direction like this.
So the plus is the X.
Mm. So basically, let's just say batteries connected in series. I'm trying to find like something that you can see easier.
Mm-hmm.
There, this one. So if you have battery and you connect it like this, okay? Positive to negative, or
Mm-hmm.
negative to positive like this will work, okay? But if you do it the other way around, like let's say here is a negative to a negative, it won't work, isn't it?
I see.
It's like it's like have you ever put battery into like your remote control or any toys that you uses electricity?
No.
If you
Oh,
connect it the
yeah,
wrong
yeah, yeah, I
way,
do.
because if you connect it the wrong way, it will not work, isn't it?
Oh,
There you go. So it has to connect this way, like positive to negative, like this. If I flip this one, negative to negative, the whole thing will not work.
mm-hmm.
All right, and then okay, now if two 1.5 volt cells are connected in parallel, okay, they're trying to explain this one. They are connected in parallel.
Mm-hmm.
The voltage at terminal PQ is still 1.5 volt. P and Q, the voltage is still 1.5 volt. It will not add up, okay?
Mm-hmm.
It will not add up. But the arrangement behave like a larger cell and will last longer. You know why? Because
No.
because basically if they connected in parallel like this, and if you have a device that uses electricity, let's say a lamp here, okay, it
Mm-hmm.
will take away only half of the electrical energy from each of these batteries, right?
Mm-hmm.
Instead of like it take the whole electrical energy from this 1.5 volt, they will have to give only half, isn't it?
Mm-hmm.
So this battery will last longer. Okay, do you know like there's something called um, door lock battery? Ever seen something like this at your door?
I do. Yeah, I do.
Mm. So those things actually lock according to the battery, okay? And sometimes it requires like four, sometimes it requires like eight battery. And it should last you a long time. But when you hear like beep, 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 you should definitely change them. Otherwise, you will be locked out of your home, okay?
Okay.
Definitely you should change it when it say beep, 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 something like that.
That's why my father always leave a window open to be in case.
Mm. Okay, there's still a way to help you get inside your home. Yes, but you wouldn't risk that, right? When it asks you to change, you should definitely change the battery. Okay, so these battery actually are connected in parallel. They are not connected in series, as you can see here. Because if in series, the positive had to be connected to the negative one here, like in a line, right? But here it's connected in series, just like this.
Mm-hmm.
I mean, in parallel, just like this. And because there are four battery here, it should last quite some time, like maybe 1 or 2 years.
1 or 2 years.
I think so. It depends on how good your battery are. I often use like what is it
I
called?
only I only use one brand. It's like it looks like it's like
Energizer?
black, red, and then white color. The black, red, and white color.
Energizer?
Yeah, Energizer. Yeah.
I like Energizer. They are really good.
I only use that brand because it's only there. I only
Mm,
see brand everywhere.
yeah, I like it because it's really good.
Is it?
Now, I think it's really good because all the battery is just really bad. It dies very quickly.
Mm-hmm.
Mm. Okay, so since they are connected in parallel like this, when when they die, all four battery will die together, okay?
Mm-hmm.
And but when they last, they will last quite some times.
I see.
Now, the potential difference at the terminal of battery decreases slightly when the current is drawn from it. Of course,
Mm-hmm.
it's like your device is sucking away the current from the battery. So of course, the potential difference will slowly decreases until it dies.
Mm-hmm.
This effect is due to the internal resistance of the battery, which transfer electrical energy to heat as the current flows through it. So imagine, you know that when you use your phone for many hours, your phone will heat up, right?
Mm-hmm.
So inside your phone, there's a battery, of course. Everything that uses electricity will heat up,
Mm-hmm.
and the battery will also heat up too. because inside a battery, there's also a resistant. And it means the battery uses some of its electrical energy to create that heat.
Well,
Okay. So it means that the battery itself uses some of its own energy, okay?
mm-hmm.
Right. Now, let's say the greater the current that is drawn away from the battery, the larger the loss voltage. When no current is drawn from the battery, it is said to be an open circuit and its terminal PD is maximum. This maximum voltage is termed the electromotive force, EMF, of the battery. And like the potential difference, EMF is measured in volt. So EMF is also in volt, just like potential difference. And can be written like electromotive force is equal to the loss of volt plus the terminal potential difference. So in energy term, the EMF is defined as the number of joules. How many joules of chemical energy transferred to electrical energy and heat when one column of charge passes through the battery or cell? All right, there's some okay, they say here if the size of the bundle Mr. Column is carrying when he leaves the cell would be smaller if the internal resistance were larger. So it means that here, back to Mr. Column here. So the battery itself has a resistance, okay? If the battery resistance is higher, it uses its own electrical energy a lot more as
Mm-hmm.
heat. And so
Mm-hmm.
Mr. Column will leave this battery with much less in his bundle. As a result, the lamp will receive much less electrical energy. It won't light up that much, isn't it?
Mm-hmm.
Mm. So what I'm trying to say is that um, any device that you use, at first when you bought it, it seems that it runs very quickly, like your phone, for example.
Mm-hmm.
But after some times, it becomes slower and slower and slower, right?
One.
It's very similar to what I'm trying to say, because slowly it gains resistance. Just imagine if you have an old machine,
Mm-hmm.
it heats up very quickly, right?
Yeah.
So because the older the machine is, the more the resistance inside of its battery. So you just use it for like 10 minutes, it heats up like a stove.
For real?
Yeah, sometimes it's like that.
It's like few hundred, like 100 degrees.
Sometimes, yeah, I'm not kidding.
So,
Sometimes it's like that. So that's why I think people should replace their laptops from time to time. Yeah. It's not meant to last forever though.
but uh, you can just reset and then it's completely to like new again.
Well, one way to do it is to replace the battery. You can just
Mhm.
replace it with a new battery, you know?
Then it won't heat up that much.
Yeah,
Oh.
because the new battery will not have that much resistance, you know? It won't heat up that much. But remember, your laptop also has other components that can heat up as well, like a CPU, GPU, something like that.
Mm-hmm.
All right, I'm talking like I'm a pro. And
Mm-hmm.
imagine if your computer is really old because its internal resistance actually increases. So it uses a lot of that energy that you feed into it to create heat. So less energy can be used for productive work.
Mm-hmm.
So slowly your laptop is becoming like a heater, you know. It's like we bought the laptop to work, right? But after some years, it becoming more like a heater.
Why my friend said that why would you make a product that it will why would you make a product that it will break that you know that it will break in the future? It's like
Well,
just so
this is capitalism. They want us to buy more and more and more so they can sell more to us. Capitalism,
so they are able to make it like not
not
break
durable.
like not breakable.
Of course, they can make it unbreakable, but if you use it for like 10, 15, 20 years, then they won't make that much profit. It's all about profit, about money.
I see.
People are very greedy.
So if you ask someone to make a durable computer that it will last very long, it will be
Mm.
cost a lot, right?
It costs a lot, but in the long run, it's a good investment. It's a good investment because you don't have to change your laptop so many times. And it's also good for the environment because
Mm-hmm.
there won't be a lot of trash, isn't it?
Mm-hmm.
Okay, now I have a question for you. Now, if you have a very old fridge and a new fridge, which one would consume more electricity and make your bill really big?
Both
Of course, the old one, because the
because
old fridge has more resistance, right? So it produces a lot of heat and it eats up a lot of electricity. So that's why keeping the old stuff sometimes is not a good idea. Oh, just remind me I have to replace my fridge. You know,
how old
maybe I
is
should, yeah, maybe I should replace my fridge from time to time.
how old is your fridge?
I'm not so sure, probably like 5, 6 years, I think. But
5 to 6 years.
every year there are new technology that help us save energy.
Mm-hmm.
All right, we have the practical work here and voltmeter in certain series and parallel here.
Mm-hmm.
Okay, let's say we have a 1.5 volt cell here, and you have a 1.25 volt lamp there, and you have a voltmeter.
The voltmeter.
Okay, so you have an amp meter is to measure how many ampere or measure the current, isn't it? So you have a
Mm-hmm.
voltmeter to measure the potential difference or the voltage, how many volt between
Mm-hmm.
2 points. Remember, potential difference must be the difference between two different points, right? Like
Mm-hmm.
point A and point B, for example, here, this point, and that point, for example. Of course, when the electricity flow through the lamp will eat up some energy, isn't it?
Mm-hmm.
So the electrical energy at this point on the left here, this point, will be more than the electrical energy on this point, right? On the right.
Mm-hmm.
Because the lamp eats up some of that electrical energy already. So the voltmeter is there to measure the difference between these 2 points. Is it understandable?
Yeah.
Mm. Good, good. You got it.
Much.
Hmm. Now, let's say you have a 4.5 volt source like this, many
Mm-hmm.
battery connected together, and you have three light bulbs like this. Okay, so of course it's the same current flowing through them, isn't it?
Mm-hmm.
Hmm. But at each of these lamp, it eats up a little bit, right?
Mm-hmm.
It's just like Snow White. going to the house of the seven dwarfs, and she's like, "Oh my God, there's a lot of food. Let's eat a little each, right?" So let's say you have a lot of electrical energy here at this point, X here. It get eaten up a little bit after it passes L1, a little
Mhm.
bit more after it passes L2. And
Mhm.
finally, after L3, there's gonna be not much energy left, isn't it? To go back to the battery.
I see.
It's like just imagine this one like a buffet, like a buffet. What's it
I see.
called? What's a buffet when the thing just like circling around? What's it
What?
called?
The buffet?
Yeah, there's a buffet when the thing just keeps circling around you, yeah, and you just pick it up, yeah. What's it called? I forgot the name of that.
Mhm.
Ah, sorry, excuse me, but I need to use my Vietnamese now. Ever seen something like this? There. So
Oh,
basically,
okay.
this thing they
Yeah,
just
I saw this
flowing
in Japanese
around.
before.
Yes, they will flow around like this, and you just have to pick the one that you want to eat, right?
Wait, then how do you like how do they um check if the people is gonna pay like how much the people is gonna take?
I think
How do
when
they
you
check?
are when you enter the restaurant, you already paid. You have to already pay, yeah.
So it's always a buffet.
It's like all you can eat.
All you can eat.
I think all you can eat, and you can stay there for a few hours if you want to.
Is it good?
It depends on where and how much money you spend on it. But to be honest
Can
with
you
you,
just stay there for the whole day and save your money?
don't do that.
Would they kick me out?
They will try to kick you out somehow, because it's not good for business. Because if you run a restaurant, you wouldn't want your customers to eat so much food, right? Because they
Mhm.
already paid, isn't it? Okay, but the point here is after okay, these food after it travel through each customers, they will pick some dishes, right?
Mhm.
So the same thing happens here. Let's imagine it like that buffet. Now, if it passes through the L1, it takes away some energy. Passes through L2, it takes away more energy. And if it passes through L3 lamp, it takes even more energy. So afterwards, when it go back to the battery, there will be much less energy. Is it understandable?
Yeah.
Yeah, it's like from the kitchen, the food passes through the customer, they take it. So after three customer, it go back to the kitchen again, like empty plates, isn't it?
Mhm.
So the same thing happens here. All right. If you have something like this, okay, what do you make of it?
Where
Okay, this one.
it looks like
Hmm.
it's supposed the whole so it goes through the whole thing and then it goes out.
Like it's like 1.5 volt, and then it goes through here, split up into two, right?
Yeah, I see. It's like that.
Yeah, split up into two parallel circuit here, and it go back to the battery. Okay, so V1 is the voltmeter that will measure the potential difference in these 2 points.
Mm-hmm.
V2 is the voltmeter that will measure the potential difference in these 2 points again.
Mm-hmm.
So imagine the electrical energy where when it passes through here, of course the current will split into two, right?
Mm-hmm.
But finally, the current will converge in this point again and go back to the battery. And it divided into two.
Mm-hmm.
Okay. So it means that the difference in voltage between this point here and this point there is still
Mm-hmm.
1.5 volt. Doesn't matter if you connected 100 lamps or whatever, or only two lamps. The difference between these 2 points is still like 1.5 volts. You know what I mean?
Mm-hmm. Yeah, I know what you mean.
Yeah. Let's just say that you have two customers sitting here, but at a kitchen, you're provided only like 10 dishes. Now, if
It's
two customer coming in, and let's say there are 10 customer coming in,
okay.
and if they sit like this, they still receive only 10 dishes. And there will be 10 empty plates going back to the kitchen, right?
Mm-hmm.
So for parallel, it's like that.
I see.
The difference in potential difference between the 2 points is gonna be still 1.5 volt here. Okay, you understand it now?
Yes.
Good, good, good. You got it. However, look at this example again. You can see that as the electricity passed through L1, some of that voltage is eaten up by this L1, right? So it won't be 4.5 at this point. It will be by, let's say, 3 point something. And after passing through L2, it will be like 1.5 something. And after passing through L3, almost zero, back to the battery, isn't it? Because they're in series, isn't it? It's in series. But if it in parallel,
Parallel.
parallel everywhere is the same, you know, almost.
I see.
You get it now, right?
Yes.
Okay, great. You got it. It's a very difficult concept, but you got it. I'm very proud of you.
What really?
It's a really difficult concept to understand, to grab, you
I
know.
find it easy
You
because I
think
eat
so?
food.
Wow. Wow.
Does
Okay.
is the buffet good though? Like the rolling buffet. Is it for Japanese people? Is it
Um,
all
you can
Japan?
find them in a lot of places in Saigon as well.
But is it good?
Yes, if you pay like up to 500,000 down, I think, per person. But to be honest with you, be ready to get like a stomachache.
Why?
Because let's say that yeah, you have to serve a lot of people, a lot of dishes. It's difficult to keep the quality, food quality. And so
Mm.
a lot of these food are just frozen, they just have to be reheated. And sometimes the seafood itself is not very clean.
Is it all sushi and sashimi? Is it is
Yeah,
it
so I'm really scared of eating the sashimi because those are raw fish.
I see. What
Yeah,
but the people sitting near to the sitting like the nearest points of the
of the food,
food,
yeah.
yeah, they will get all of the good food first.
Yeah, exactly.
Then how will they
Okay,
like
if you go in a group, maybe they are kind enough, they will get the food for you, maybe.
wait is it can you like order the food?
I think yes, you can actually order more food beside from these.
I see.
Right. Okay, let's come to this part. Voltages around a circuit. Now, we were talking about series, right? This one, this one series. So, in the previous experiment, you have found that in the circuit of this figure B here, the total voltage is actually equal to V1, which go to here, plus V2 would go to here, and V3 which go to here. So let's just say 1.5 volt, 1.5 volt plus 1.5 volt. It's going to be 4.5 volt here, right?
I see.
Hmm. So they say the voltage at the terminals of a battery equals the sum of the voltages across the devices in the external circuit from one battery terminal to the other.
Oh my God, why does studying make me so hungry?
Because of this.
I'm
Okay,
craving,
just half an hour, okay? Just half an hour more.
I'm so
Okay.
hungry.
So, okay. Just ask dad to have some food for you afterwards, okay?
Yeah, I want to eat chicken.
Now that you mention it, it's been some time since the last time I ordered something. Oh my God, I'm so poor this year. Oh my God.
Or,
Everyone is struggling this year, okay?
oh yeah, did you heard about a new virus in China?
Oh my God, the pneumovirus things.
Does it have the potential to be as big as Corona?
I don't think so, but it's just really annoying. You don't want to get sick, okay?
I hope it's like as as like as powerful as Corona,
Why? You want
so
people
that
to
I don't
die?
go school again. And like there's lockdown.
Come on, you want people to die?
I mean, uh, like I don't know.
All right, so parallel circuit. So they say that V2 here will be equal to V1. You know why, right?
No, why?
Okay, I was trying to explain to you. So even though the current here has to split into two, right? But the voltage is the difference in electrical energy. Let's just say at these 2 points. It doesn't matter how many times it splits out. The difference between this point and this point is still the same, right?
Yeah.
Like for example, if you have 100 candies, okay, and you have to give to 10 friends, and if you have 100 candy, but you have to give to 20 friends, the whole class will only receive the total of 100 candies, right?
100
Is it
candies.
understandable?
No, can you explain it like
Okay. Once again, let's say if you have, say, 10 dishes of sushi, and there are two customers sitting here like this, okay? They will eat a lot of those sushi, and so you get 10 empty plates back to your kitchen, right? Now, let's say if three more customers entering and they sit like this, parallel,
mm-hmm.
but you have only, let's say, one chef, so you can only give them like 10 dishes of sushi to begin with. Doesn't matter how many customers coming in, right?
Mm-hmm.
So at the end, you still receive 10 empty plates, right?
Yeah.
So what does it say here? V1 is equal to V2 here.
V1 is equal to V2.
In parallel circuit, yeah. In parallel circuit, it doesn't matter how many branches. The potential difference between the 2 points is still the same.
I see.
Now you understand. That's why I say V1 is to V2. So the voltages across devices in parallel in a circuit are equal. Okay. Is it a lot of headaches already?
No, just making me more hungry.
Okay,
Hungrier.
let's do this one now. You have a question number one. Can you read that?
The PD across the lamp is in figure 37.6 is 12 volts. How many joules of electrical are
Electrical
changed
energy
into
is
watt
change.
of heat when it charged?
Mm,
One C
mm.
passes through it. What's 1C again?
One column.
Oh, one column.
Mm.
Mm,
So you remember the formula? So, okay, so 1 volt equal to 1 joules over 1C, right?
mhm.
So you can flip it around. So electrical energy E equal to the volt times the column. Okay, so this one is 12 volt to begin with, okay? They ask how many joules of electrical energy are changed into light and heat when a charge of one column passes through it. Try it.
Can I have a 5 minute rest? I have to
Yeah,
take.
sure, sure.
I'm thirsty.
Mm. Okay, let's try this one again.
Give
Okay,
me a crack.
so
Made it. I
hmm?
just ate a cracker and it made me more hungry.
Okay,
And the apple.
so okay, let's start thinking about crackers. Let's try to use number one, okay? Now, so you have a formula. You know that 1 volt equal to 1 joules divided by one column, isn't it? So rearrange this one. You have 1 joules equal to 1 volt times 1C, right?
Mm-hmm.
Now, they ask, okay, they give you 12 volt to begin with, and they ask how many joules of electrical energy are changed into light and heat when a charge of one column passes through it. So you know you have 12 volt to begin with and one column. How much energy is that? How many joules? When 12 volt and one column, how much energy, how many joules is that?
Mm. 1 volt equal 1, 2, 3. 1 volt equal 1. 1 joules. Is it one?
No, it's actually 12 joules. Because you
Oh.
start with 12 volt, right? And you have
Mm-hmm.
one column, so 12 times 1, you're going to have 12 joules, isn't it?
Mm-hmm.
Okay, now let's try when a charge of 5 column passes through it.
Mm,
How much you have?
uh, is 100. No, yeah, 110.
Not that much. So you have 12
No,
volt.
no, 50, 60, 60.
It's 60, yeah. It's 60 volt because 12,
I
no,
miscalculated.
60 joules, sorry, 60 joules. So 12 volt times 5 column, you get 60 joules to begin with. Now, if you have a current of 2 ampere flows in it for 10 seconds, this is a hard one. You have to use another formula. So you have a formula here, energy equal to current times time times voltage. Okay. And now they ask you how many joules of electrical energy and you provide current of 2 ampere, 10 second. Okay, you do it.
Where 2 amperes low heat for 10 seconds.
Okay.
20? No.
Don't forget to times the volt as well.
Uh, 240? No.
Yes, 240. What's the unit?
Ampere?
No, they ask for joules. How many joules? So the unit must be 240 joules. Remember, units are very, very important because let's just say $10 or 10,000 Vietnam dong. That's different, right?
$10 or what?
Let's just say that $10,000 and 10,000 Vietnam dong is different.
Yeah.
Big difference, right?
Yeah, it's a big difference.
Of course. So energy, oh, sorry, okay, so the units of joules, volt, ampere, whatever is also important. You must be exact with those, okay?
Mm-hmm.
Now, you understand what we are doing now? You seems to.
Yeah.
Now, let's go to number 2. So you have 3 2-volt cells are connected in series and used in the supply for a circuit, okay? I think it's better if I just paint. Okay. Sorry, I'm just old style.
It's okay.
You're welcome. Okay, so let's just say 2-volt. Oh, I need something like it's weird. I think Paint they updated their interface something. It looks very different from the last time I did it. Oh my God. Brushes. Okay, let's just say natural pencils. Okay, so 3 2-volts that are connected in series. So let's just say first you have one of them. This is
Mm-hmm.
another one. And you have another one, right?
Uh-huh.
So 2-volt. This one is 2-volt. This one another 2-volt also. And this one is another 2-volt. They're connected in series and used as a supply for a circuit. Okay. So they ask what is the potential difference at the terminal of supply? So which means like from here to this point, what is the potential difference? You answer.
Mm,
They're in series, okay?
uh, mm,
We did something like that before. So when they're in series, they combine together. So it's gonna be 6-volt in total. Okay, but if they are in parallel, how many volt in total if they're in parallel?
no.
So if they are 2-volt each of them in parallel, what is the potential difference at these 2 points? You answer. The answer is 2 volts
Mm,
because in
Volt.
parallel, right? So remember,
Yeah.
in circuits, they add up. Okay, in circuit, the voltage they add up. Okay, but in parallel circuit, in series circuit, they add up. But in parallel circuit, they do not add up, right?
Hmm.
Okay, if
It is
you review it, you understand why, okay? So I think I suggest that we continue from this point onwards next time, okay?
okay.
Right, okay, I'm just gonna don't say, okay, just gonna